Have you ever seen a chemical element play detective? In this video we're diving into the properties of iodine, a humble purple-gray solid that can do extraordinary things. We'll explore 3 eye-catching experiments featuring iodine: growing shiny iodine crystals out of thin air, performing the famous iodine clock reaction that ticks down to a sudden color change, and using iodine fuming to reveal hidden fingerprints, like a CSI Pro. Along the way, we will highlight iodine's special properties, like how it easily turns into a violet gas, sublimation, and its knack for reacting in dramatic ways with other substances. By the end of the video, you will see that iodine is not just essential in your diet, it's also the star of chemistry class and forensic science. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also make sure to fill in the poll in the post section of the channel for next week, as we will be discussing another element. Now, safety first. Iodine and its reagents can be hazardous. In all these experiments, we'll be wearing gloves, goggles, and work in a well-ventilated area. Avoid inhaling iodine vapors or skin contact with chemicals. Safety first. Our first experiment looks like pure magic. We will grow iodine crystals out of thin air. Now, how is that possible? Well, the secret is iodine's ability to sublime, to jump straight from a solid to gas, and then reverse sublime back to a solid in crystalline form. Now, in other words, iodine can go directly from a solid chunk to a beautiful purple vapor without melting into a liquid. And that vapor can deposit onto a cool surface as solid crystals. We're going to harness that trick to create spectacular iodine crystals right before your eyes. The first is 2 big spoons of copper 2 sulfate and 3 big spoons of calcium chloride. Copper 2 sulfate is a beautiful bright blue crystalline salt. When it's dissolved in water, it creates that iconic vibrant blue color you see in so many chemistry labs. In this reaction, the copper ions will act as our oxidizing agent, which means that they're the ones that will kick things off by taking electrons. Our third chemical is potassium iodide. This is a simple white salt, but it's our source of iodine. It's actually the same compound used to iodize table salt, just in a much more pure form. The iodide ions in the salt are the ones that are going to be oxidized. They'll give up their electrons to the copper, and in doing so transform into the elemental iodine we're here to see. We also have a fourth chemical on standby, sodium thiosulfate, and this isn't for the main reaction, it is for cleanup and safety. It's a neutralizing agent that will safely react with any leftover iodine at the end, making disposal much easier. Now, for the equipment, we'll be using a standard glass beaker as our reaction vessel. It's made of borosilicate glass, so it can handle the heat we're about to apply. The goal now is to gently heat it over this burner, not to set it on fire. Just raise the temperature nice and steady. But the most critical part of gear for growing crystals is the cold finger. That's just a fancy term for a cold surface that we can introduce to the hot vapor. I'm using this special cold cup, which will fill with ice and cold water. Now, the huge temperature difference between the hot iodine vapor and the cold surface of this cup is what will trigger the deposition. The magic of turning gas back into a solid. The greater that temperature difference, the finer and more intricate our crystals will be. This is the formula we are about to see. Now, the important part for us is that the iodine is being liberated as gas, hence blooming of purple vapor inside the container. So here we now see the gas, and the iodine gas cools down when it hits the cold surface and loses energy. Suddenly it can no longer remain as a gas and deposit as solid iodine crystals. You'll see them appear like magic, shiny, metallic-looking, purple, black crystals growing on the underside of the cold surface, seemingly out of thin air. They often form delicate needle-like or plate-like shapes that sparkle when you light them. We've essentially created a tiny iodine crystal garden from nothing but vapor. Now, what happened here is iodine demonstrated a phase change called deposition, the direct transition from a gas to solid. We bypassed the liquid phase entirely. Iodine is one of those substances that readily sublimes solid to gas, and likewise deposits from gas to solid, because its molecules aren't strongly attracted in the solid, allowing some to break free as gas even at moderate temperatures. So this is like when you have a cold morning, water vapor can deposit as frost on a window. However, water vapor is invisible and forms clear droplets or frost, whereas iodine's vapor is a conspicuous purple and its crystals are dark and lustrous, making the transformation much more dramatic. Now, to make sure we got the crystals, we had to keep the setup dry. We actually included a drying agent called calcium chloride in the container. Why did we do that? Now, because moisture in the air could condense on our cold surface as liquid water, that's not what we want, and disrupt the crystal formation. The calcium chloride is hygroscopic. It grabs onto water vapor and keeps the air dry, so that only iodine vapor is at the cold surface. This is why only iodine freezes out, not water, yielding pure iodine crystals. Now, this experiment raises the question, does iodine actually have a liquid phase? Well, it does. Iodine can exist as a liquid, but you'll almost never see it in the lab because its melting point is 114 degrees Celsius and its boiling point is just 184 degrees Celsius. That's a pretty narrow window, only about 70 degrees, where iodine is a liquid. At room temperature, it prefers to skip that liquid state and sublime directly from solid to gas. That's why in our experiment, we got straight from shiny crystals to purple vapor, without any puddles of liquid iodine in between. So while liquid iodine is real, it's more of a laboratory curiosity than something you will encounter in everyday experiments. So let's talk a little bit about the history, how humans first discovered this colorful element, iodine. It turns out that our little experiment is similar to the original discovery of iodine in 1811. According to legend, French chemist Bernard Courtois was processing seaweed ash looking for compounds for gunpowder. Now, legend has it that while he did this, his pet cat knocked over a bottle of sulfuric acid into the mix. Now, the seaweed ash contained iodide salts, much like our potassium iodide, and the sulfuric acid, a strong oxidizer, somewhat like our copper 2 sulfate in effect, reacted with them. Courtois was astonished to see clouds of purple vapor rising from the container, which then crystallized into dark, shiny flakes. A new element had been born. So iodine quite literally announced itself as purple smoke. We can thank that clumsy cat for one of the most vivid elements on the periodic table. Now, the cat story is probably a myth, but I like cats, so I'll take the myth. Now we need to clean up this safely. Remember the sodium thiosulfate that we set aside? Well, we now use it by rinsing the crystals and any iodine-rich surface with it. Thiosulfate reacts with iodine, converting iodine back to colorless iodide ions. This neutralizes the iodine, making our cleanup safer. No purple stains or lingering vapors. The spent solutions, now containing iodide and other innocuous products, can be flushed down the drain with plenty of water per proper disposal guidelines. Now, for our second experiment, we're turning iodine into the star of a color-changing clock. If you ever wanted to time something with chemistry, this reaction is a classic, though as we will see, it will be a pretty terrible cooking timer, unless you like surprises. This demonstration is famously known as the iodine clock reaction, originally discovered by chemist Hans Heinrich Landolt in 1886. It's a brilliant way to showcase chemical kinetics, reaction speeds, because two clear solutions mix, nothing seems to happen for a while, and then BAM! The liquid suddenly explodes into a deep blue-black color, as if on cue. So here is the setup. We actually need to prepare two separate solutions, which we will call solution A and solution B. So this is how we make solution A. In a beaker, we dissolve about 0.2 grams of sodium metabisulfite and about 50 milliliters of warm distilled water. We also add a small amount of starch to this solution, around 0.1 or 0.2 grams, just a pinch. And the warmth helps the starch dissolve and also the metabisulfite to dissolve fully. Now, what are these for? Now, the metabisulfite provides bisulfite ions in a solution, which will act as a timer reset chemical. You'll see how in a moment. The starch is our indicator. It's like the dye that will reveal iodine's presence by turning blue, black, when iodine shows up. Right now, solution A is clear and colorless. Starch may make that slightly cloudy until fully mixed, but essentially colorless. Now here we have solution B. In a separate beaker, we prepare the oxidizing solution. We dissolve about 0.7 grams of potassium iodide in 70 milliliters of distilled water. Potassium iodide will provide iodate ions, which are a source of iodine in a higher oxidation state. This solution B is also clear and colorless. Now for the reaction, we pour solution B, the iodate, into solution A, the bisulfite starch mixture, and stir them together. At this moment, we start the clock. Initially, the mixed solution remains clear and colorless, looking like plain water. We can stare at it, perhaps with a stopwatch running, and it seems like nothing is happening. But don't be fooled. A quiet chemical race is on. Now, after a delay of several seconds, the exact timing can vary, often on the order of 10 to 30 seconds, depending on the concentrations, suddenly the mixture erupts into a bold dark color, typically black-blue, or deep purple color, like ink. The change is almost instantaneous when it happens. Now, this is startling and very satisfying to watch, right? One moment it's water-like, and the next moment it's like someone added a bottle of dark blue dye. That dramatic color is due to the iodine and starch forming the well-known iodine-starch complex, which is an intense blue. We've effectively set off our iodine alarm. How does this work? Well, so what happens was that during the introduction period, when the solution was clear, this iodine clock actually involves a sequence of reactions, some fast, some slow, that together reacts as a timer. Here's a simplified explanation of that. And the first one is a slow reaction. It's like the clock ticking. In this mixture, the iodate from the potassium iodate is reacting with the bisulfate from the metabisulfite. This reaction slowly produces iodide ions. One way to write this is this. Now, in essence, the iodate is being reduced by the bisulfite, generating a little bit of iodide. This is the rate-determining step. It proceeds at a controlled, slow pace, which is why nothing obvious happens at first. Then we get to the fast reaction, the invisible handoff. As soon as any iodide is produced, it can react with more iodate, which is still abundant, to produce iodine. However, the moment iodine appears, the bisulfite present immediately reacts with it and reduces it back to iodide. Think of bisulfite as a diligent janitor cleaning up any iodine the instant it forms. Specifically, one possible set of fast reactions in our mixture, and that shows like this. Iodate quickly oxidizes iodide into iodine. Bisulfite immediately reduces iodine back to iodide. So, the net effect? Iodine is being produced and consumed over and over, staying at extremely low levels. The solution stays colorless because any iodine that could have colored is instantly mopped back up into iodide form. We essentially have an invisible cycle where iodine pops up and vanishes before our eyes can detect it. As long as there is bisulfite around to reduce the iodine, the blue starch reaction can't happen because there's no free iodine accumulating. The surprise finish. Time's up. The clock runs out. When the bisulfite is completely used up, exhausted, after a certain period, the slow generation of iodide from step 1 has consumed all the bisulfite in converting iodine back. At that moment, the very next speck of iodine that forms has no savior reagent to convert it back. So iodine finally accumulates. The moment even a tiny excess of iodine is present, it immediately binds up with the starch in the solution, forming the starch-iodine complex that has that dark blue color. Thus, the solution suddenly changes color, signals the time is up. It's like an alarm bell of our chemical timer. Now, the delay interval of this weird clock can be tuned by changing the amounts of concentrations of the certain reagents. For instance, if we add more thiosulfate or bisulfate, in some version of this experiment thiosulfate is initially included, the delay before the color change is longer because there's more capacity to consume iodine. Conversely, if we use less, the color will appear sooner. Temperature and concentrations of iodate and iodide sources also affect the speed. Chemists love this demonstration because by measuring the time to color change under different conditions, you can learn about reaction rates and kinetics. Now, why is this a terrible cooking clock? Well, I'm not going to explain the joke here, but I could not find any application for the use of this experiment. If you do know an application for this experiment, let me know in the comments. On the lighter side, the dramatic side of the iodine clock reaction makes it perfect for impressing students or party guests. The sudden change can even cycle back and forth in some variations, though our version stops at black-blue. Landolt discovery in 1886 has since spawned many variations of the clock reaction. Some using hydrogen peroxide and iodide, others using different reducing agents, but they all share the same principle of a delayed color reveal involving iodine. It's a beautiful example of chemical timing, and it highlights iodine's role in a redox reaction as a color-changing indicator via starch complex. Our final experiment takes iodine out of the beaker and into the world of forensic science. This is where iodine earns the title as OG element that CSI uses to find fingerprints. Long before modern detectives had fancy powders, laser, or super glue fuming, they had iodine. Now, in fact, the technique of using iodine vapors to reveal latent fingerprints dates back all the way to 1863, when Professor Paul-Jean Coulier in Paris first published a method for fingerprint developing using iodine fuming. And that makes it one of the earliest, if not the earliest, chemical fingerprinting methods in history. And guess what? It's still used today in forensic labs because it's simple, quick, and non-destructive to evidence. We're about to show you how it works. To reveal fingerprints, you actually just need a source of iodine vapor. Professional forensic kits sometimes use an iodine fuming wand, loaded with iodine crystals that sublime or fuming cabinet. We will do it in a chemical reaction to produce iodine, similarly to our first experiment, but without the heating. Here's what we need. First, we need the copper 2 sulfate, about 5 grams, which we've used earlier. The second thing we need is potassium iodide, about 1 gram. This is the white salt that we used earlier in our first experiment. Then we need some distilled water, just a few milliliters, about 3 would be enough to dissolve the potassium iodide. And then we need a piece of paper with a latent, invisible fingerprint on it. First, we place the 5 grams of copper sulfate powder in a large beaker or wide mouth jar. In a separate small cup or beaker, we dissolve the 1 gram of potassium iodide in the 3 milliliters of water. It will form a clear colorless solution of iodide ions. Now, before we mix them, we need to prepare some fingerprints. Now, for that, you take a clean sheet of white paper and firmly press a few fingers on it, especially if your fingers are a bit greasy. If they're not too clean or dry, fingerprints might be faint. Forensic experts sometimes rub their fingers or their nose or forehead to pick up some skin oils before making a print. Now, the next step is to put several good thumb or finger marks on the paper. These prints are invisible for now, just the natural oils from your skin left on the paper. Now, we're ready. Now, to reveal these prints, pour the potassium iodide solution into the beaker with the copper sulfate. Immediately, a chemical reaction kicks off. You will notice the mixture might turn a cloudy brownish color and possibly even see a bit of orange-brown solid. Now, what is happening here chemically is the same reaction we used earlier with the copper sulfate and the potassium iodide. Iodine is formed. So here again we have the formula that is balanced out. The iodine forms potassium iodide, giving electrons to copper 2 plus ions, reducing them to copper plus, which forms copper iodide, a pale solid. Now, in the process, the iodide is oxidized into iodine. That iodine immediately makes the solution brown because iodine, especially iodine 3 minus, in solution has a yellow-brown color. More importantly, iodine vapor starts to rise from the liquid. You might see a faint purple haze above the solution or just smell that distinctive iodine smell, like old antiseptic. Now we take the paper with fingerprints and suspend it over the beaker, fingerprint side down, exposed to the iodine vapors. You don't want the paper to touch the liquid, just hold it or support it so that it's in the iodine-rich air above the reaction. If your beaker has a wide mouth, you can lay the paper across the top. If it's a smaller opening, you might tape the paper under a lid or a rig, something to hold the paper in contact with the fumes. We leave the paper in place for 10 to 15 minutes to allow the iodine gas to do its work. This is a great time for a bit of patience. Maybe dim the lights and shine a flashlight obliquely on the paper to better see any developing prints. Now, as the minutes pass, you will start to see a fascinating result. Orange-brown fingerprints appear on the paper, where previously there was nothing visible at all. The fingerprints will gradually develop, revealing the whorls and ridges of the finger marks. It feels a bit like developing a photograph. By the 10 to 15 minute mark, the prints should be clearly visible as orange-brown patterns against the white paper. Congratulations, you've developed latent fingerprints using iodine, just like forensic teams of the late 19th century. Now, our result was a little bit less spectacular, so what we've done is we've used the UV light to show you the result a little bit better. Now, how does this work? Well, the science behind it is both simple and interesting. Iodine has a high affinity for oils and fats. The residue left behind by your fingerprints, sweat, skin oils, fatty acids, will readily absorb iodine vapor. Iodine molecules are nonpolar and dissolve nicely into oily substances in the fingerprints residue. Now, when the iodine gas hits the paper, it doesn't stick much to the paper fibers. Paper is polar cellulose. But it does stick to the greasy fingerprints deposit. So the ridges of your fingerprints accumulate iodine, and that iodine color, brownish orange, marks the fingerprint pattern visibly against the background. It's essentially a temporary staining of the fingerprint by iodine. This is a physical absorption, not a permanent chemical reaction, which is why it's temporarily. The iodine will eventually sublime away from the print into the air again, and the print will fade. In fact, within 30 minutes to a few hours, depending on the conditions, an iodine-developed print will completely disappear as the iodine evapors off the oil. This ephemeral nature is a double-edged sword in forensics. On one hand, it's non-destructive, the print fades on its own, or can be removed quickly by heating, so the paper isn't permanently altered and can be preserved or treated with another method later. On the other hand, it means that investigators have to capture the print quickly, usually by photographing it before it vanishes. For a more lasting record, forensic scientists often fix an iodine-developed fingerprint by spraying or painting the paper with a starch solution after fuming. You might recall from the iodine clock experiment that starch reacts with iodine to form a blue-black complex. Now, this happens to fingerprints too. If you treat the print with starch, the iodine in the print forms that deep blue starch-iodine complex, turning the print dark and much more stable. It can last for weeks or months after that. It's a cool crossover between our experiments. The starch that helped signal iodine in the clock can also make iodine-developed fingerprints visible for longer. Historically, starch was indeed the first method used to stabilize iodine-developed fingerprints as early as the 1900s. Modern labs might use other chemicals like benzoflavin or treating with heat and photographs to preserve or record the prints. But starch is a cheap and effective fixative if needed. Now, even it's a quite old technique, it's still widely used for certain applications. It's especially useful for porous surfaces like paper, cardboard, or raw wood, surfaces that don't take regular fingerprint powder well. And because iodine doesn't permanently alter the evidence, the prints fade, investigators often use it as a first step. Fume with iodine to get a quick look, take photos, and later you can then apply a different chemical like ninhydrin or DFO to the same paper to get another read, since iodine left no permanent trace. Now, this is also attractive because it's cheap and simple. All you need are some iodine crystals, or in our demo, just potassium iodide and copper sulfate to generate them. No fancy equipment required. Even a Ziploc bag can serve as a fume chamber by adding iodine crystals inside with the paper. In the early days, crime scene investigators used something called an iodine fuming gun, basically a tube with the iodine crystals. By warming it and blowing through, they directed iodine vapor onto surfaces. These days, they have electric wands and chambers, but the chemistry is still the same. Now, finally, for the disposal, we take the leftover mixture in a beaker, which is dark brown now. It contains iodine and copper salts, and add a spoonful of sodium thiosulfate. This is also what we should have done with the iodine clock reaction, just like before. The brown color faded as thiosulfate reduces iodine to iodide, and the solution can be flushed away safely with lots of water. The paper with iodine, if not fixed with starch, will lose its color over time. Iodine evaporates, and that's normal. So why iodine and not something else? Well, iodine behaves this way at a molecular level. Iodine's bag of tricks comes down to its atomic structure. First, sublimation. Iodine exists as diatomic molecules. These molecules are held together in the solid by relatively weak van der Waals forces compared to the stronger bonds inside the molecules themselves. Because those intermolecular forces are weak, iodine can escape directly from solid to gas once it has a bit of energy, and that is why it sublimates so readily. Second, iodine forms colored complexes thanks to its large polarized electron cloud. When iodine interacts with molecules like starch, charge transfer interactions occur. Electrons are slightly shifted between iodine and its surrounding molecules. This alters how the complex absorbs and reflects visible light, producing the deep blue-black color that makes the clock reaction so striking. Finally, iodine's nonpolar and fat-soluble nature comes from the fact that iodine molecules are electrically neutral and symmetric. They don't have a positive and negative side like water. That makes them hydrophobic, but it also means they dissolve easily into other nonpolar substances like fatty oils left behind in fingerprints. At the microscopic level, iodine molecules literally slip between the hydrocarbon chains of skin oils, becoming trapped and concentrated there, which is why the fingerprint's ridges darken so clearly under iodine fumes. Now, throughout these experiments, iodine has proven itself to be a truly remarkable element. We've seen it change state in the blink of an eye, from a solid crystal to a purple gas and back again, demonstrating the exotic feat of sublimation and deposition. We've watched it orchestrate a delay chemical drama in the clock reaction, hiding in plain sight and then revealing itself with a stunning color change. And we've applied it to a real-world problem, unmasking hidden fingerprints, as if by magic. A trick that's been used by detectives for generations. From creating crystals out of thin air to timing a reaction to revealing secret fingerprints, iodine has earned its place as a classic and versatile element. We hope you enjoyed this deep dive into the world of iodine's chemistry. Now, if you think we missed anything, let us know in the comments, and if you want to know more about iodine, make sure to watch this video about the element next.